Last week, we showed that aperiodic monoids define the same languages as first-order logic, which is the same thing as LTL, which is the same thing as H-trivial monoids. H-class, if you remember, is an intersection of a prefix class and a suffix class. So a natural question is, what about other trivialities? For example, what about suffix trivial monoids? Or, a stronger property, what about infix trivial monoids? Now, infix trivial implies suffix trivial implies aperiodic, and therefore both suffix trivial and infix trivial should correspond to some kind of restrictions of either first order logic or LTL, and they will. And this is what we're going to show in this lecture. So let's begin with suffix trivial. Of course, prefix trivial is going to be symmetric. So the logic that's going to correspond is going to be a fragment of LTL, which I would call LTL with finally only. What this means is that you're not allowed to use until, but you're only allowed to use finally. Finally, if you remember, means in some future position, but not right now. So, for example, a position satisfies finally A if there's an A in the strict future, not necessarily right now. Okay. We will also use other derivable formulas such as finally star, which means now or in the future. So it means phi or finally star. And a dual one, which is globally, which means in all strictly future positions. And the globally star, which means, well, now and in all strictly future positions. Since all of these are defined in terms of f, I would just call the logic LTLF. So here let's write some example formulas. The formula finally A is true in a word if and only if that word has some A in the future. So it's A sigma star. Remember, we say that a formula is true in a word if it's true in some position of that word. We can also say that the word has length at least 2, which means I can go once to the future and once again to the future. Well, actually length at least 3. We can say that a word contains a subsequence, say, of the form ABC. Here it doesn't matter if I use strict or not strict until. Strict means without the star and not strict means with the star. So this is words which have A followed by B followed by C followed by something. In fact, you can say the word contains ABC, but it does not contain any longer word, and that therefore means that the word is exactly equal to ABC, and therefore in the logic we can define every finite language, because we can describe every word uniquely, and then if the language is finite, we can just take the union over all words in that language. So this is a logic, a fragment of LTL, and as we shall see, it's roughly speaking equivalent to suffix trivial monoids. There's a little bit of an annoying thing, which let's do it right now, which is that it's not exactly equal to suffix trivial monoids for the stupid reason that the formula A, it's an LTLF formula, which doesn't even use F. It describes the language, words which begin with sigma, with A. Now, this monoid is not suffix trivial. The syntactic monoid of this language is not suffix trivial, nor any recognizing monoid is not suffix trivial, because if you take any word that begins with A, and then you can add letters to the left and it starts to begin with B, and then you can do it again and it starts to begin with A, and so on, and therefore you can get words in any recognizing monoid there will be words that begin with A and words that begin with B in the same suffix class. So such a recognizing monoid cannot be suffix trivial. But that's, roughly speaking, the only problem that can appear with this logic. As once the formula leaves the first position, then it becomes suffix trivial. And in fact, if you look at all of these languages here, the formulas begin with F or F star, and therefore they're going to describe suffix trivial monoids. If you look at these languages, all of them are recognized by suffix trivial monoids. So now we're ready to give the main theorem about suffix trivial monoids, which is the following theorem. The following conditions are equivalent for a language. Recognized by some suffix trivial monoid. All of the monoids here are going to be finite, so it's a finite suffix trivial monoid. Let's write another one which is kind of obvious, but it's maybe useful to remember this. The syntactic monoid is suffix trivial. These two are clearly equivalent. Well, if the syntactic monoid is suffix trivial, then some recognizing monoid is suffix trivial. But for the converse implication, you can, if you look at the Michael-Nerodi theorem, it says that if you take any recognizing monoid, then you can get the syntactic monoid by first restricting to a submonoid, namely the image of the corresponding homomorphism, and then taking a quotient. So the syntactic monoid of a language can be obtained from any other recognizing monoid by taking submonoids and quotients. Quotient means the image of a surjective homomorphism. And it's kind of easy to see that if a monoid is suffix trivial, then any submonoid is going to have the same property, and likewise any quotient. So if you take any recognizing suffix trivial monoid, you're going to get the syntactic monoid out of that, and it's going to be suffix trivial. And this is going to be a general theme. So recognized by some monoid with property blah blah blah, if and only if the syntactic monoid has property blah blah blah, as long as the property is preserved under submonoids and quotients. And this is going to be true for all of the properties discussed, most of the properties discussed for some time. Okay, but so far nothing has happened. Now is the main thing. It's the connection with logic. So can be defined by a Boolean combination of formulas of the form sometime in the future phi, where this uses only LTL with the finally operator. And actually there's going to be another condition, which is can be defined by a finite union. It's going to use regular expressions, finite union of regular expressions of the following form. So you write some alphabet star here, then some letter, and some other alphabet, star, and some letter, and so on. Like this. But not any expression of this form is going to qualify. It needs to be unambiguous. And unambiguous means that AI does not belong to sigma I. So that means that there's exactly one place to put this A1 because it's the rightmost place with the letter A1. And likewise, there's exactly one place where to put A2, which is the rightmost place with an A2, which is before the rightmost place with an A1, and stuff like that. So these kind of regular expressions, and I will call them suffix unambiguous. So let me maybe give you an example. Well, let's first do it like this, and actually the proof is going to go like this, and like this. So this is the theorem. So let's maybe give you an example of some suffix and ambiguous expressions before we continue. So for example, you can say it ends with some B's, and then there's an A. This A is in a unique place, namely the last A. And then maybe there's some A's and B's. And then there's a C. And now there's some B's again. And now there's a C. And now there's some maybe A, B, star. This is an example of a suffix and ambiguous expression. Okay. So let's start the proof. We begin with from the syntactic monoid to a suffix trivial language. So let's begin with syntactic monoid is suffix trivial implies that it's a union of suffix and ambiguous expressions. Now, before I continue, there's a nice thing about suffix and ambiguous regular expressions. It follows from the monoid, and maybe it's not completely obvious if you look at it for the first time. So if you take a language and it's recognized by a suffix trivial monoid, then the same is true for the complement. So the class of languages recognized by a suffix trivial monoid is closed under complements. In fact, it's also closed under unions and intersections, and therefore it's closed under arbitrary Boolean combinations. But let's focus on complement. It follows that if a language is recognized by a finite union of regular expressions, which are suffix and ambiguous, and the same is true for its complement, because this class is closed under complement. So will be maybe nice to notice. Let's begin with this thing. So the main lemma is as follows. So imagine you have a suffix unambiguous monoid, and then you have a sequence of elements in this monoid. And it has some product, say B. What we're going to show is that this product can be computed by a union of suffix and ambiguous expressions. So the main lemma is the following. We take a finite monoid, which is suffix trivial, then for every element of the monoid, the language words that would have product A is a finite union of suffix and ambiguous expressions. Okay. This will imply that every recognized language is such a finite union, because if you take a homomorphism into a suffix trivial monoid, then you take the accepting set, then you take the words in the monoid which have a value, a product in the accepting set. This by the lemma is going to be a suffix, an ambiguous expression, and then you substitute, instead of the monoid elements, the letters of the input alphabet which get mapped to those elements. And if you think about this substitution, it's consistent with the condition, defining condition about an ambiguity, so it's going to be fine. So let's prove this lemma. So let's prove the lemma. The proof, no surprises here, is going to be an induction on the position in the suffix ordering. So it's induction on the parameter number of b's, such that b is a proper prefix, proper suffix of a. The induction base and the induction step are proved the same way, so let's just take some a, and let's assume that we have already found expressions for all strictly simpler b, and let's construct such an expression for a. Now it's actually quite simple. So to see this, consider a word w which has product a. So this means that the entire word has product a. Now, some prefixes of this word might have product b which is not equal to a. And if this happens, then b has to be strictly smaller in the suffix ordering. So we can apply the induction assumption. Now take the suffix which has a different product, b not equal to a, but which is maximal for the property. If you take that suffix, then the next letter, which is going to be c, will have the property that you add the next letter and its product a again. A corollary is that every suffix which contains the c is going to be between a and a in the suffix ordering, and therefore it will have to be a again. Okay? It means that if you look at these letters, they are in the following set, which let me call it maybe sigma 0, which is letters d such that d product a is equal to a. Because each of these letters, it takes a back to a again. Okay? So what we have just shown is that a word has value a, product a, if and only if it can be decomposed as follows. There is a prefix which has these words that preserve a. Then there is a c. And then there's a word with product b. And this is for some choice of c and b, such that cb is equal to a, but b is strictly smaller than a. So in particular, it's not equal. So this is our expression. It's a finite union, and all it remains to show is that this expression is suffix and ambiguous. Now, what we do is just for the product b, we apply the induction assumption. We get some expressions. We distribute the concatenation across the union, and we get a new regular expression. And it's suffix unambiguous. For that, we just need to argue that if you take any one of these expressions here, and it begins with some, say, gamma star, then you cannot have C in here. And that is true because if this expression inductively obtained, which defines B, would begin with some gamma star that contains C, then adding another C to it wouldn't affect the result, but it should, because adding C to B will give you A. So this completes one part of the proof. Now let's show that a union of suffix unambiguous expressions is in fact definable in the logic LTL. By a Boolean combination of formulas finally star phi, where phi uses only LTL with the finally operator. And this is kind of obvious again. Actually, all of the things are obvious here. Let me just do it on an example. Suppose that you have sigma 1 star. Let's do it in full generality. It doesn't really matter. So we have a suffix unambiguous like this, expression like this. In general, it's a finite union, but the formulas also have finite unions, so we only need to care about the single one, and define Li to be the prefix, the suffix of the expression, which ends with sigma 2. So the entire expression is ln plus 1. Okay? And by induction we show that ln is definable in the logic. So how does ln, well, li plus 1, what is it? It's sigma I plus 1 star ai li. Now, so suppose that there's a formula phi, which is like this. Now let's first of all try to define this part. So what is it going to be? It's going to be, my label is ai, and some future position satisfies phi I. This is still not enough, but what I should do is a stronger thing, and every future position satisfies phi I or a smaller one. Okay, so call this psi I. So this defines ai followed by li. Now psi I has the nice property that if it holds somewhere in the word, it holds in a unique place. There's only one place where you have the first ai after li. Therefore, we can now define phi I plus 1, which is the one for phi L, to be as follows. All I have to say is that if I look at the unique place that satisfies ai, so then the positions before psi I have labels in sigma I plus 1. And this you can write as follows. You write globally star if in the future I see psi I, then I must have a label. And then you also have to say that I actually do see psi I. Maybe even in the first position. And that's the appropriate formula. Okay. So now the last thing we need to show is, so we've done this, we've done this, and now we're going to do this. This is actually kind of very simple. So let's maybe prove it here. So we want to show that if it can be defined in the logic, then the monoid is suffix trivial. A Boolean combination of. And we're going to prove the contrapositive. So if it cannot, so here is not, and here is not. Okay. So what does it mean that the syntactic monoid is not suffix trivial? That means that there exist elements A and B which are in the same suffix class. So it means that if I start with A, I can get to B, and then I can get to A again, and so on. Well, that's it. Okay. If the syntactic monoid has this property, then that means that if I think of y, x, a, and b as words, then these words can be distinguished in some context. So it means that there exists an environment such that if I put in w1, yx, let me even put it like this. This is going to be A, and this is going to be in the language. But if I take B, then it's not in the language. So if this is here thinking about A, Y, X, this is what it means for the syntactic monoid to be not suffix trivial. These are witnesses for this. And now we can exploit this by observing that these two words cannot be distinguished by any formula of the form finally star f phi, where this uses only finally. And roughly speaking, the idea is that if you run such a formula on one of these two words, then because of this initial finally star, it's going to jump to some place, maybe here. But then there would be an equivalent jump here. This requires a little bit more formalization, because if you jump here, then you need to show that you need to jump here with a suitable position of x, but it's not a difficult argument to show. So this is just an easy Ehrenvoigt-Freise argument. So these two words cannot be distinguished by formulas of the appropriate form, and therefore the language cannot be defined by this logic, which establishes the contrapositive. So we have thus finished the characterization of suffix trivial languages. And as I said before, prefix trivial languages are defined the same way, except that you use a logic which goes instead of finally to the future, it goes finally to the past. So we now move to describing the languages which are described by infix trivial monoids. This class, I think, is more interesting than the ones for suffix or prefix trivial ones, and the corresponding theorem was proved initially by Simon, but it has developed Simon and Imre Simon from the Simon theorem, but it has developed since, and I'll try to present to you a modern version of Simon's characterization of infix trivial monoids. And this modern characterization, it's very strongly based on an important concept here, which is the Higman ordering. So the Higman ordering is the ordering where you take words, say A, B, A, C, and then you just add letters in between. So you keep the A, B, A, C, but maybe you might add some new letters like B, B, A, C. You don't need to add letters everywhere. A, B. So I will write the Higman ordering like this. So if this is W and this is V, then I will write like this. You don't need to add any positions. So W is embeds, I could call it like this, embeds into itself. Now, the main property of the Higman ordering is Higman's lemma, which is why it's called the Higman ordering. And the Higman's lemma was called like this because it was proved by Higman, shockingly. Which says, well, there's several ways of saying it, but I would put it like this. For every upward closed set and upward closed means that if a word is in L and there's a bigger word, then the bigger word is in L as well. Actually, the upward closed set is generated by a finite subset. So that the upward closure is the set, well, this is L itself. Yes. So this is the U up arrow is the upward closure. This is Higman's lemma. And it will play an important role in our characterization of infix trivial languages. But before we do that, let's observe the following corollary of Higman's lemma. For every language, it doesn't even have to be regular, well, it will turn out to be like regular, is L is upward closed if and only if L is definable in what I would call exit star first order logic. And what this is formulas which are of the form X exists an element, exists another element, and then here you have a quantifier free formula. So this is existential first order logic. Now, why is a corollary true? Well, clearly, if you are definable, well, both parts are clear actually. If you are definable in first order logic, then you're clearly true, you're closed under inserting letters, because the quantifier free part will remain true if letters are added. And it's important here that it only uses the order, it doesn't have a successor. Successor could be violated by inserting positions. That covers the right to left implication. But for the left to right implication, we see that if L is upward closed, then by Higman's lemma, it's the upward closure of a finite set of words, which means you belong to the L if and only if you're Higman greater than word W1 or word W2 or word W3. Being Higman greater than some fixed word is definable in existential first order logic, so being Higman greater than some finite list of words is also definable in the logic, and that gives us the left to right implication. So it turns out that if a language is upward closed, then it's actually already regular. In fact, a very simple form of regular. Now, these upward closed languages are going to play an important role in our characterization of infix trivial languages. So let's state this. The following conditions are equivalent. So number one, recognized by a finite infix trivial monoid. This is going to be equivalent to something that is called piecewise testable. And that just means a Boolean combination, a finite Boolean combination of upward closed sets. As it's stated now, this result was originally proved by Imre Simon, but I will add another condition which is due to other authors, and we'll get there later. But before we do that, let me explain the name piecewise testable. The idea is that a language is a Boolean combination of upward closed sets if and only if it's a Boolean combination of upward closures of finite languages, if and only if it is a Boolean combination of upward closures of individual words. So that means that a word belongs to the language if and only if there's some fixed testing set, and you just ask, this guy embeds in W and this guy does not embed in W, or maybe W3 embeds in W, or W4 embeds in W. That kind of conditions. The Boolean combination of conditions. Somebody is Higman smaller than me, or somebody is not Higman smaller than me. That's what a Boolean combination of upward closed sets is. Now these things are originally called, I believe, by Simon pieces, hence the name. But let's forget that. Now there is another thing, and it will actually be useful, namely zigzags. So let me define let me first state it. There is no infinite zigzag between L and its complement. So what's a zigzag between L and its complement? It's simply a sequence of words such that you begin with L, you now are not in, you make it bigger but you're not in L, then you make it bigger again and you're in L again, and now you are not in L again, and you continue like this forever. So it's an increasing chain, doesn't have to be strictly increasing chain, which alternate between L and L. Now, okay, if L and L, well, it has to be strictly increasing, because if you're not in L, then two consecutive words cannot be equal because one is in L and the other is not in L. However, there's a more general notion of a zigzag between languages L and K, so it alternates between L and K and L and K and L and K, and there maybe if L and K have non-empty intersection, it could be not strictly increasing. So what we're going to show is we're going to first show this equivalence, and then we're going to show this equivalence, and therefore Szymon's original theorem will follow. So let's begin with the bottom part, and actually for the bottom part we'll write an even stronger result, which was proved by Czerwiński et al., which is the following thing. You take two languages, think of them as being disjoint, think of them as being L and its complement, or more generally disjoint languages, then the following conditions are equivalent. Number one, there are zigzags between L and K of arbitrarily large finite lengths. So maybe not an infinite zigzag, but it can be as long as you want. LK, 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 LK. Condition 2, well, there's actually an infinite zigzag. And number 3, L and K can be separated by some piecewise testable M. So what that means is that you have L here, you have K here, and this piecewise testable M contains L, but is a disjoint with K. Now, I hope that it's clear that this blue lemma, which I will call the zigzag lemma, implies this equivalence. If you apply the zigzag lemma to L and K being the complement of L, then you know that there is no infinite zigzag between L and K, if and only if L can be separated from its complement by some piecewise testable M. Now, how can you separate something from its complement? Well, the separator has to be equal to L, because there's no space in between. So if L can be separated from its complement by some piecewise testable M, it means that L itself is piecewise testable. And therefore the zigzag lemma establishes the black equivalence on the top of the screen, this one. So let's prove the zigzag lemma. And it's kind of nice, because if you look at the proof, it actually uses no properties of words except the ones given by Higman's lemma. And in fact, it would be true if sigma star is replaced by any abstract set, and Higman's ordering is replaced by any ordering on that abstract set, which has the property from Higman's lemma, which is known as a well quasi-ordering. But let's not be too general. So 1 implies 2. If there are zigzags of arbitrary large finite lengths, we want to create an infinite zigzag. And the way we do it is as follows. Define a graph G, where, so this is the graph, vertices are words from L, and then there is an edge from one word to another. If you can go from W to V, passing through some word from K. If there exists some U in the K, such that W embeds in this intermediate word, and then, so this word is in K, and then you go to V. So it's a graph on L. Now, our assumption says that G has arbitrarily long paths. And we want to show that it actually has an infinite path. So, let's define L omega to be the words which have arbitrarily long. Well, no, okay, let me put it maybe a bit more. Maybe define it differently. Define for W, define its potential is, it's a number which could be omega, which is what is the upper bound on the paths, least upper bound of lengths of paths that begin in W. So if alpha is 2, it means you get a path of length 3 but not of length 4. But if alpha is omega, it means you get paths of whatever length you want. Now, if W embeds in V, then any path that begins with V can be converted into a path that begins with W. So it means that the potential of alpha of W is bigger than the potential of alpha of V. Now, we know that potentials are unbounded. Furthermore, L has finitely many minimal elements with respect to the Higman ordering. This is, roughly speaking, this equivalent to what the Higman's lemma says, because you take the upward closure of L, it has finitely many minimal elements, and there you go. So if you take the finitely many minimal elements of L, they will have the maximal potentials. And therefore, since potentials are unbounded, one of these finitely many elements will necessarily have potential equal to omega. So unbounded potential. Furthermore, so it follows some W, some minimal element, has potential alpha of W is equal to omega. You can see that my omega and my W look the same, which is a little bit wrong. But now if you take this word with infinite potential, and then you look at its successors, so vertices which can be accessed via one edge in the graph, and then you look at the minimal successors with respect to the Higman ordering, then one of these must have potential omega as well, because these are the guys who have maximal potential among vertices reachable from W. So this guy will also have potential omega. It follows that if you have potential omega, then you have a successor with potential omega. and so you can get an infinite path that way, as in the Koenig lemma. So this establishes that if you have arbitrarily long zigzags, then you have an infinite zigzag. Now let's prove 2 implies 3. What does this mean? That means that if there is an infinite zigzag, then you cannot be separated. And this is kind of super easy, because imagine you have an infinite zigzag, W1, W2, W3, W4, and so on. So if there would be some hypothetical separator, then this would belong to the separator, this would not belong to the separator. This would belong to the separator, this would not belong to the separator, and so on. But this cannot happen, because if this guy is a finite Boolean combination of, say, M1, MK, which are upward closed languages, then for every one of these upward closed languages, the zigzag eventually, if you look at, does it belong to M1? No, no. But then once it starts to say yes, it starts to say yes forever. So for every one of these, eventually it will always say yes, or eventually always say no. So eventually the value of M will stabilize, and that cannot happen. So this is super easy. And now let's prove 3 implies 2, implies 1, which is that if you cannot be separated by a piecewise set, then there are zigzags of arbitrarily large finite lengths. And again, here it's going to be easier to prove the contrapositive, which means zigzags have bounded length implies that it can be separated. So why is that? I think here it will be easiest to think of a picture. So this is our language L. This is K. Now define L1 to be the words in L which are the beginning of a zigzag between L and K of length 1, but no more. So it means if you start in L1, then you cannot go to K, because otherwise it will be a zigzag of length 2. Likewise, K1. L2 means you can do a zigzag of length 2, but not of length 3. So maybe there's like a zigzag which looks like this. You start here, you'd go to K1, that's fine. But that's the longest zigzag, a zigzag of length 2 that you can have. And we continue like this. So K2, it means you can have a zigzag of length 2, which begins in K and then goes to L, but does not continue anymore. But that's as long as you can get, and so on. So we stratify the languages with respect to the maximal zigzag lengths that they allow. Now, since zigzags have bounded length, this is a finite stratification. So let's say it stops at L4 and K5. Okay. What we're going to show is that these, by induction, we're going to show that we can separate each Li from each Ki. So more precisely, we're going to show that, let me erase this, that there exists a separator, say, which I want to separate L at most I, here I equals 2, from K at most I. So I want to find a piecewise testable separator which separates L at most I from K at most I. So let's draw this separator. It has to contain L1 and L2. Doesn't matter what it does with L3 and L4. Doesn't matter what it does with K2 and K3. But we do know that it separates, that it avoids K1 and K2. So this is a separator for L at most I and K at most I. And by induction on I, we will show that such a separator exists, and once I reaches its maximal value, we get something that separates everything. What we're going to show, in order to show that L and K can be separated, we will show by induction on I that you can separate L at most I from K at most I, and you can separate L strictly less than I from K at most I, and of course symmetrically K strictly less than I. So the order of events is going to be like this. If I can separate I will first prove this, and then I will prove this. This will give me the induction step. So let me first prove the bottom implication from this one. So suppose that, and in this picture I will assume that I equals 3. Okay. So I know that I can separate L1 union L2 from K1 union K2, and I want to show that I can separate L1 union L2 from K1 union K2 union K3. So there will be the following languages will be involved. First of all, I take my separator from the induction assumption, which separates L1 union L2 from K1 union L3 from K1 union K2. I have no idea what it does with 3 and 4, so it does something like this. It's a language M, which separates L smaller than I from K smaller than I. That's from the induction assumption. Now what I want to do is I want to get rid of K. You see there's this part with K3 that I want to get rid of. So what I'm going to do is I'm going to take the downward closure of K3. The downward closure of K3. Now, where can this downward closure go? Is it possible to go down from K3 and to reach K2? No, because if you go down from K3, then any zigzag that was enabled continues to be enabled. So if you go down somewhere, it has to be in K3 or K4. For the same reason, if you go down from K3, you cannot reach L1 or L2 or L3, because if you go down from K3 and you reach L, then the place that you reach is going to be in L4. So you could go down to L4, but you will avoid L1 union L2 union L3, and you will avoid K1 union K2. And I don't know, maybe you don't need to. This picture suggests that you contain all of K4, but that does not need to be the case. Okay. So now we can see that if we take M minus this thing, then it's a separator. Why? Oh, should have called it using this notation. This is Ki. Same here. Well, it's disjoint from K smaller than I, because it's clearly disjoint from Ki and K1, K2 we just argued, but it also contains well, we don't know if it contains, but it's well, this guy is disjoint. This guy here. Subtracting it will make sure that we're disjoint from case sub I, and we're not going to subtract anything from L1 and L2, so we have this inclusion remains valid. So this is the separator which witnesses this. So we're done with this implication. So now we have finished the proof of the zigzag lemma. In particular, we have proved this. So piecewise testable, equivalence to no infinite zigzag. Now what we're going to show is this, which is the equivalence with infix trivial monoids. This will take us also a little bit of work. So as we know, recognized by an infix trivial monoid is the same thing as the syntactic monoid is infix trivial. So we're going to prove two implications. The first one is recognized by some not recognized by some infix trivial monoid implies that there is an infinite zigzag, and then the second is going to be the opposite implication, which is that it is, if it is recognized, then there is no infinite zigzag. The first one is kind of easy, the bottom one. So let's start with the bottom one. So if it's not recognized by any infix trivial monoid, in particular the syntactic monoid, is not infix trivial. Which means that in the syntactic monoid you can go in infixes between two different elements. Now, if you remember what the syntactic monoid is defined as equivalence classes of words with respect to two-sided congruence. So what that means is that if we assume that you go from A to B by appending things on two sides, and then if you go from B to A by appending something on two sides, then what this will mean is that there exist words. Well, you can think of xa, y bar, and so on as being these words, and there exists an environment such that if I take A and then I do x bar to the power of n, y bar to the power of n, this gives me A, and I put that in the environment w1, w2, then this is in the language. And then if I do a similar construction but with B, then this is not in the language. And you can see a zigzag right here, because as you increase the value of n, you get words which are bigger in the Higman ordering. This guy embeds into that guy, and they continue embedding as you increase the values of n, and you get an infinite zigzag. So this part is easy. The hard part is this one. That if you're recognized by some infix trivial monoid, then there is no infinite zigzag. And Well, the key lemma here is the following. So consider, let's define an AB zigzag. These are two elements of this of a monoid. Is just a sequence of words W1, W2, and so on. All of them in the monoid, and such that this guy gives A, this guy gives B, A, B, and so on. So this is an AB zigzag in the monoid, and the lemma that we're going to prove is the following. If a monoid is, well, infix trivial, and there is an AB zigzag, then A equals B. This will imply that if your language is recognized by an infix trivial monoid, then you cannot have an infinite zigzag, because any increasing chain in the Higman ordering will need to have the same value all the time, and therefore all of it will be in the language, or all of it will be outside the language. So let's prove this lemma. And here there are again two sublemmas. So the first one is this. Let's call it claim. Claim 1. Suppose that there is an AB chain. Well, an AB zigzag. Then you can find decompositions as follows. A, B, A again as follows. So for A, I just take the first word of the zigzag. C1, C2, C3, up to Cn. And this will be copied in C. Well, I can copy actually using my super tool. But apart from these things, we're going to have some extra letters. This will be B0, B1, B2, and so on, Bn minus 1, Bn, and here I will have A0, A1, A2, An minus 1, An. So the lemma says that there exist monoid elements Ci, Ai, Bi, such that this happens. But what is most important, all of these things are going to be zigzags. So there will be zigzags of this form. So why is this lemma true? Well, the idea is as follows. You take any zigzag, AB zigzag. It's like an infinite amount of rows. Now for each row, you can see where the C1 is placed, and then you can look at the things between C1 and C2. So this is also going to be a Higman chain. If you take a row, a column between C1 and C2, it's going to be an infinite increasing chain in the Higman ordering. And by its extraction of a subsequence, you can assume that it alternates between some two elements, B1 and A1. And you do such an extraction for all columns, and you get the conclusion of the claim. So this claim is kind of easy. So we're now going to prove the lemma. So let's prove the lemma. Proof, is induction on, well, the infix ordering coordinate wise. So x is smaller, xy is smaller than AB if x is an infix of A and y is an infix of B. Okay? So let's assume that we have We take some AB. We've already proved the lemma for all xy, which are strictly smaller. Let's prove it for AB. So suppose that there's an AB zigzag. We apply the claim. And we get this. Now, if BI, well, clearly it's smaller or equal than BA, because it's contained here and here. So it's clearly smaller, but it could be strictly smaller. So let's suppose that it's strictly smaller. Then BI is equal to AI. Otherwise, it has to be just literally BA, because that's the only thing that could be smaller in an infix. Now, so suppose that we have that if all I have this, then this row and this row are the same. So we're done with the lemma. So the remaining case is that at some point we have this for some I. Now, so let's say that it's B2, I equals 2. Now, so this is B and this is A. It follows that all of these guys have the property that if you write them to the left of B, you get B again. And all of these guys have the property that if you write them to the left of A, you get A again. So we have the following summary situation. Let's maybe move this up. So we're going to have the CIs which are after and which are before. So if I is smaller than I, if j is smaller than I, then CJA equals A and CJB equals B. If j is bigger than I, we have CJ equals A and CJ equals B. If we combine these informations, it follows that C1 up to Ci, let's call this guy C, and Cj plus 1 up until the end, let's call him C prime, have the following properties. A is equal to CC prime, and furthermore, A is equal to AC, and B is equal to BC is equal to AC prime is equal to BC prime. So we have these conclusions. Okay. Now we consider now a BA zigzag. We do the same reasoning, and either we conclude that B equals A, or otherwise we get some elements. So here we got element C prime, or otherwise we get elements D prime, which satisfy symmetric properties. So the first word in the zigzag is equal to D prime, and both monoid elements are closed under adding these things. And that's all we need for the rest of the argument. So take these two, all of these C, C prime, D, D prime, and now we're ready to give the final blow. So it's A is equal to C, C prime is equal to D, C. I can add DC, the D's, is equal to, and I can continue this forever until I get a large number which is an idempotent. Now, thanks to infix triviality, I can swap this and then continue and get back to B. So I have just proved A equals B, and thus I have finished the lemma. So if your infix trivial, then every zigzag has to be trivial, which finishes the proof that if you're recognized by some infix trivial monoid, then there is no infinite zigzag, which finishes the proof of this theorem. And that's it. Thank you.